Hello everyone, welcome to second part of lecture 8 of the course High Performance Computing, Advanced Scientific Computing. The lecture 8 is Computational Fluid Dynamic. We talk in the first part about some introduction of the computational fluid dynamic, and then we will continue in the second part. In second part, we will have some short review on the flow regime and the numerical method are using in these different regimes. In the fluid dynamic, the flow has two main regimes. It's called laminar flow and turbulent flow. To identify the difference between these two regimes, there is a number, non-dimensional number. It's called a Reynolds number. And here in this slide, you can see its equation, which is a ratio of the inertial force to viscous force. Indeed, when the viscous force, in contrast to the inertial force, has a smaller difference, the flow is laminar. But when the viscous force is getting very low value, the flow will be turbulence. Then in the turbulence flow, we can say the viscosity is too low, but in the laminar, the viscosity, it has a effective roles on the flow. Indeed, the turbulent and the laminar are the feature of the flow, not of the fluid. When we look on these parameter, there are characterization of the flow, and it doesn't matter it's which type of the fluid. That way, when we are studying the turbulent flow, we can generalize and you have a universal perspective of the flow in different fluid. As an example, in this slide, you see the flow when it's passing a cylinder. On the lower figure, the laminar flow has a symmetric streamline before and after the object. We can say upstream and downstream. But when we look on the turbulent flow, when the flow passing the object, after the object, there are wake and complex streamline, which is from the von Karman street. For different Reynolds number, they behave different in the size and continuity, and this is one of the different visualization of the turbulent flow and the laminar flow. In the next one, you can see when the flow is coming from the valve, and what's happening when the flow is laminar and when is turbulence. The right hand side is the laminar one and the left hand side is turbulence, and we can see the visualization of these different behavior of the regime in the flow. The complexity of the turbulent fluid make it difficult to solve it in every scale, and still it's one of the unsolved problems. The another concept in the fluid dynamics is a compressible and incompressible. In this slide, you can see the left-hand side figure showing how when we have the compressible flow and incompressible flow, when we have the external force. And the comparison on the table, we can see when the flow is compressible, that means the fluid, it can be compressed, the volume can be reduced, the density can be changed, and the Mach number as a non-dimensional number used for this kind of the flow should be greater than 0.3. But when we have incompressible flow, it cannot be compressed, the volume cannot be reduced, density cannot be changed, and the volume of the Mach number is less than 0.3. The compressible and incompressible flow also is categorized in the fluid dynamic, You can see in this flowchart when the categorize when there is a constant density, then it's hydrodynamic and incompressible aerodynamics. And also when we have the compressible flow or gas dynamic area, the density is variable. You can see the presentation of the fighter when it's passing the sound speed, and it's called this phenomena the sound barrier. That means when the object passing the sound speed, and this is happening. Therefore, we can say these concept of the compressible make two category of the fluid depend of the density, which is a variable or constant. Then after to have this short description of the concept in the fluid dynamic, now let's have a look of the instruction of the CFD and how we are using the different approaches. The first one is the finite difference method, which must has consistency, stability, and convergence. There is a classification method for PDEs. We call them hyperbolic, parabolic, and elliptic. To solve this equation, the boundary condition and initial condition are required in different way. Indeed, in the finite difference method, the domain of the problem discretized to a small element or meshes, as you can see here in the center of the slide, and each grid will has a name or index, and we will solve the problem for each of these index or each grid. Then all of the solution for every grid will be collected to present the solution for whole of the domain of the problem. To solve the given PDE by excuse me, by numerical methods, the partial derivatives in the equation approximated by finite difference relation. The finite difference equation is algebraic equation and will write for each grid point within a domain. The solution of the finite difference equation provides the values of the dependent variable at each grid point. And if we want to see how we make the finite difference technique for a problem, these steps should be taken. We have the physical model, then we will write the governing equation with boundary condition, initial condition, then the domain of the problem will be discretized. The system of the algebraic equation will be created. Then in numerical methods to solve the system of the algebraic equation, there are different methods. Also, we will talk about them. Using the computer to solving this algebraic equation and the post-processing. So this is the main steps to use the finite difference method in the CFD. The most important part is the solving by computer. Depend to the size of the problem. Imagine how the size of the problem and how the size of these meshes. We will have many grids, then many algebraic equations. To specify the size of each mesh, which here is delta y and delta x, you can see in this slide, we choose this size in a way that the solution meet the consistency, stability, and the convergence, especially the stability. There is a specific term and method to specify them. We are not going on this detail since we are not teaching the CFD in this course, but this point to show depend of the size of these meshes, we will have a different number of the grid. With much more number of the grid, we will have much more computing. So it will be essential to have high performance computing to solve this type of the problem. Also, there is an explicit and implicit term in the numerical scheme, which is mean when we are using the explicit method, there is a one unknown for the problem for algebraic equation, but when we are using in the implicit one, there will be more than one unknown in the algebraic equation. The finite difference method has a scheme that covers the consistency, stability, and convergence. For example, from the explicit method, there is a forward time or central space, which is conditionally stable. There is a default Frankel scheme, which is unconditionally stable. From the implicit method, there is a Lassonant scheme and Crank-Nicholson. However, the point regarding the implicit and explicit, it is implicit methods offer great stability since more than one unknown appears in the algebraic equation and require more computation time per time step. At this point, it shows if we are using the implicit method, we will have great stability, then it will reaching the great solution. However, because the number of the unknown will be more than one, then the algebraic equation will need more computation time. Here, the HPC help us to perform it faster. Regarding the size of the meshes, the grid size and time step are both directly affect the stability and consistency. Also, the time step and grid size impact the computation time. So we can see here, if we want to get the stability and consistency, we should choose the right grid size and time step. Also, if we have small sizes of these time step and grid size, the computation will be too high, especially when we have 3 dimensions. So it's very important to choose the optimum size of the grid and time step to be able to run a solution to have a stability, consistency, and also appropriate computing time. Then we must choose the grid size and time step to meet the stability condition and to perform the suitable computation time. Regarding the algebraic equation, we said in the previous slide, we need to use the solving method. There are different methods. There is a direct method, which like lower upper decomposition, Gaussian elimination, matrix scaling, Gauss-Jordan elimination, and also about the iterative methods, Jacobi, Gauss-Seidel method, successive over relaxation, which is called SOR. Also, we have the Thomas algorithm for diagonal matrix algorithm is called TDMA. These are different methods we need to have in the computational. Of course, when we are using the coding and programming, each of these methods has a specific code we need to write for it or use some. For example, in the Fortran program, we have some specific subroutine to use to solve this type of problems. Then we have a different step. Then we are discretizing, creating the algebraic equation. We need to check the stability and consistency of the equation. And then we can use one of these solving methods to solve the linear algebraic equations. The next method is the finite volume, FVM, which is relying on the element type. In the finite volume method, the volume integrals in partial differential equation that contain a divergence term are converted to surface integral using the divergence term. As you can see, the domain of the problem discretized to a small element, and in the finite volume method, the grid or the point that's solving the problem is the center of each element or mesh, and then using the solution for each center mesh and collect the solution for all the domain. There is also a specific coupling on the finite volume method when there is a pressure and velocity coupling, staggered and collocated grid. Usually on the staggered grid, the scalar variables such pressure, density, total enthalpy are stored in the cell center of the control volume, whereas the velocity or momentum variable are located at the cell faces. And you can see it's presented on this figure in the right hand side. This is the difference from a collocated grid arrangement where all variables are stored in the same position. So this is the difference between a staggered and collocated method. The staggered storage is mainly used on the structured grid for compressible or incompressible flow simulation. So this capability of the staggered, it makes it used broadly to solve this type of the problem. This is one of the advantage of the finite volume method when there is a pressure velocity coupling. Also in the finite volume, there is a different volume structure for 2D and 3D problem. Usually the finite difference method, has a weakness to use it for the complex geometry. Usually you use it for the simple geometry and regular grid. But the finite volume and also finite element that we will talk next after the finite volume, they are usually used for the irregular meshes, which we can say unstructured. Here in this slide, you can see these different structured and unstructured and how the meshes sizes and meshes geometry are different, and the computation also should be different for them. The finite volume also has a different structure. For 2D there are 2, and for 3D there are 4. You can see how they look like and when discretizing the domain of the problem. So the scheme for the finite difference and finite volume are different because the capability of the finite difference is limited to a structured one, but the finite volume it's able to deal with the unstructured also. In the previous slide, we saw there are different structure of the volume to discretize and meshing the problem. Then when we are dealing with this problem, it is important to know use which one of these volume, for example the quad one or the hex grid, what degree of the grid resolution is required of the domain, how many cells are required for the problem, and these questions are important because also we need to know how the sufficient computer memory and also about the computing. Usually there are some general statements. For example, for simple geometry, quad and hex mesh can be provide high quality solution with fewer cells than a comparable with the tree and tent mesh. For complex geometry, quad and hex mesh show no numerical advantage, and usually it's best to use the tree and tent meshes. So these statements helping us to use the correct meshes to have the meshing on the domain of the problem. In the left hand side you can see example how using the meshing to discretize a problem. Sometimes there is a concept of the symmetry. When we have the symmetry problem, we're trying to reduce the computing. Then for the symmetric one, we're dividing the domain of the problem and solving for the problem, for example, of the half of the problem or sometimes quarter of the problem, and then extend it for the whole of the domain of the problem. There are different techniques need to use on the CFD to be able to run the simulation and reduce the memory of the computer and also reduce the computing time. Also, one of the important issues in the CFD is the boundary condition. Boundary condition is crucial of any mathematical model, especially on the fluid dynamic. If you look on this example, for example, these two cylinders, one of them has a surface boundary, which is a common wall, it's type wall. But when we look on this next one in the left hand side, it has an inlet and velocity inlet. So this is a different, we need to use different boundary condition, because we will have the outlet from the pressure for this one, but for the without inlet we don't need the outlet. For the multiple exit also, you see this example here. The left hand side is showing the velocity inlet 1 and there are 2 outlets. The right hand side there is it's showing that we need to have the velocity and pressure inlet, and from the outlet we need the pressure of 2 of these outlets. Then the boundary condition is crucial, and we need to have this information. Without having this information, solving this type of the problem will be so complex, and we need to make some assumption to be able to solve this type of problem. So in addition to meshes, size of the meshes, type of the meshes, we need to have the condition, the boundary condition of the problem, which what meaning on the beginning, if we assume at the beginning time 0 time, what the condition to be able to run the problem properly and get the right solution for it. About the scale complexity in the CFD also, there are many terms need to be taken into consideration. Fluid dynamic covers a broad range of the physical phenomena, but the majority of flow is a turbulence, and we can say the broad range of the scale of the motion with non-linear interaction. Indeed, the flow has a random motion and non-linear. However, sometimes some flow are repeatable and predictable. So, depend of this feature, we need to use the right method. Let's have a short introduction to talking about the RANS and LES and DNS method. As we said, the majority of the flow is a turbulent. In the turbulent flow, because of the different behavior than the laminar regime, we are dealing with different scale of the element of the flow. We call them eddy or coherent. Because of this different scale, when we are choosing the mesh or size of the element, that we talk them in the different approaches, finite difference method, finite volume method, and finite element, the volume or the element or the mesh should cover these different scale of size of the turbulent flow. Depend of the complexity of the flow, we need to take decision that we need the average solution of the problem or we need the exact solution. Therefore, in the CFD, there are 3 approaches to deal with this complexity of the scale in the turbulent flow. One of them called Reynolds average Navier-Stokes. This one extracting the average solution for the problem, not the exact solution. For example, if we have a very fine and very teeny scale, maybe we don't get the detail for the problem on that scale. Then the next one is the large eddy simulation. It's called in the term LES. Large eddy simulation provide much accuracy than the advanced. However, in the large eddy simulation, we are using some filtration and we're solving a problem with a specific scale, not for the all scale. Then we don't have the all solution for all scale of the problem. The next one is the direct numerical solution. It's called DNS. DNS solving the problem in the whole scale, and it's one of the exact and high accuracy solution. However, based of these categorization of the scale, DNS is the expensive one. LES is cheaper than the DNS, but it's so costly than the runs, and the runs is the cheaper one. Because of this difference, usually the runs method used in the industry, and it's provide the sufficient information that is required for the engineering design, and it costs much lower than the LES and DNS. The next one usually used in the research is LES. DNS, however, used in the some research, but because of its cost computing, we're trying to don't use it as much as possible. But in the essential cases, DNS is used. Here, for example, for the predictable cases, we show that the runs 10 to 5 times cheaper than the aliens. That is very important, especially when we have the large problem. The 10 to 5, it's not something that we can neglect it, and it's so different cost. But when we can use the runs and we cannot, there is no actually cases that say when we can use it, but it depends to the many experience and many statement that is available in the literature, and of course who is using the approach. This slide presenting the different solution between the runs, LES, and DNS. In the right hand side, you can see the runs, Reynolds average, Navier-Stokes, presenting the average solution for its example of the jet, turbulent jet. We can see a large eddy simulation, LES, presenting much more detail on this case in contrast to the runs. But the last one, direct simulation, is presenting all the detail and all the scale of the problem. So this is the difference of the solution between these methods. These three categories presenting different results. However, the most difference between them the computing cost, and it's very important depend of the application to use which one. About the parallel computing that we are using in the CFD, based of the dimensional of the Navier-Stokes, number of degree of the freedom active in a turbulent flow at Reynolds number, and we can calculate. You can see number of degree of freedom is Reynolds to 9/4. Based of this, we can understand how much computing is required, because the number of degree of freedom is presenting how number of the grid or element that we have. For example, most of fluid has this feature of the viscosity, the velocity larger than 1 meter, and the length scale also 1 meter. And usually the Reynolds number for the turbulence flow exceeds the 10 to 6. So the number of degree of freedom is 10 to 13. This is the order for the degree of the freedom. And in the computer processing, usually we calculated flop per second, floating point operation per second. If we assuming the floating point operator per second is executed in a single clock time, t, the clock time is a second, the processing speed, it will be in this arithmetic presentation, f over t. Now let's see an example of this regular turbulence flow for the CFD model that we have a Reynolds 10 to 6. And the number degree of the freedom is 10 to 13. Then assuming each degree of freedom takes 300 flop in a single time step, these mean 10 million gigaflop per second is required, and is about half a year to compute just a single time step. Here it's showing us how the computing the turbulence flow is costly and it's complex, and we need the high performance computing to deal and solve the problem in this area. And this is just with some assumption we get to these calculation. Then one of the approach, as we said, we're making the discretization of the problem, and also we make a decomposition in parallel computing for domain of the problem. Here you can see this example when we have this domain, an example of the heat transfer. The domain decomposition is happening between 6 processor 1, 2, 3, 4, 5, 6. We assume that we need to solve this problem on a very large grid, especially with 20,000 by 20,000 grid. Then the storage requirement can be estimated as follows. You see the grid point, 4, 10 to 8, and bytes per number. There are 8, and number per node are 2. Then we will have 6.4 gigabyte requirement of the storage to solve this type of problem. And this is a very simple calculation to see for 2D problem but how many storage is required to solve this type of problem with domain decomposition. And then there, so far we had introduction and the CFD and the review of the laminar and turbulent flow and compressible and incompressible flow, and how we can using this concept of the Reynolds number, which is specifying the regime of the flow, which is laminar turbulence, to make the discretization and decomposition of the domain of the problem to be able to run the problem in the parallel computing. And here is the, in this slide, it's a very simple presentation of this decomposition. As a reminder, you remember in the open form example, in the lecture 4.2, we use the decomposition to run the simulation of the problem on a full processor. Indeed, the decomposition of the domain, it's what we did here is presented, and you saw we had used different technique also to make the solution in the open form. And this is indeed the fundamental and the principle of the parallel computing for the domain in the CFD. Here we finish the lecture 8, the second part, and in the end there is a video. I suggest you to watch it to see how we can use the high performance computing on the cloud for the CFD problem, and actually presenting the perspective and the future of the high performance computing, which is essential, as you saw in the workshop of the real scale cloud computing, that how you can have access to parallel computing via the cloud system. Then this was lecture 8. So we had this introduction about the CFD, and in the next lecture we will talk about the most unsolved problem as a turbulence flow, to emphasize on the why we need to use high performance computing to deal with this type of a problem. So see you in the next lecture, and thank you.